This video is on valence electrons and Coulomb's law. So in the previous lesson, we talked about the difference between all of the electrons and just the valence electrons. Valence electrons are those electrons in the outermost energy level. All the other electrons are considered core electrons. We're going to focus on those valence electrons because those are the electrons that are responsible for how an atom acts or reacts in situations. So it's important to make some generalizations about the number of valence electrons that an atom can have. We looked at members of group 1 yesterday and saw that every member of group 1 had one valence electron. Then we looked at the electron configurations for magnesium and calcium, so members of group 2, and saw that those elements had two valence electrons. And it turns out that all of the elements in group 2 have two valence electrons. So that makes it pretty easy to remember group 1 and to have the same number of valence electrons as their group number. And we'll see if that trend continues here. So those short columns, the transition metals, those have a varied amount of valence electrons. And we'll address this a little bit more as we go into bonding. So now we're going to go to those taller columns, so group 13. And group 13, the boron family, has 3 valence electrons. Not quite as easy, but maybe we can see if there's a pattern here. So group 14, the carbon family, has 4 valence electrons. Group 15 has 5 valence electrons. We looked at oxygen as a representative of group 16 and saw that it had 6 valence electrons. The halogens in group 17, have 7 valence electrons. And most of the members of group 18, the noble gases, have 8 valence electrons. And so even though the number of valence electrons is not the same as the group number, there is a relationship there. Basically, if we take the group number in 13 through 18 and subtract 10, we get the number of valence electrons. Or just drop the 1, either way you want to look at it. Now, remember, 8 valence electrons is the magic number of stability. And atoms are going to form compounds in order to try and get to 8 valence electrons. That is one of the reasons that the halogens in group 17 are so very reactive. They have 7 valence electrons. They are so close to having 8 that they can taste it. And a lot of times what the halogens will react with is members of the alkali metals, group 1. Because their 1 valence electron added to a halogen's 7 valence electrons adds up to give us 8. And that would be true in like sodium chloride or table salt. You've got something that has 1 valence electron, the sodium, and then the chlorine has 7 valence electrons. All right, so now what we're going to do is we're going to talk about Coulomb's law. This is going to help us understand the reason behind all of the periodic trends that we're going to be discussing in this unit. Coulomb's law has to deal with attractive and repulsive forces. And that's really all the trends that we're going to be talking about. Most of the time, we're going to be talking about those attractive forces. So how the positive nucleus is attracted to those negative electrons in an atom. Now, Coulomb's law depends on 2 things. The first thing is the charge, and it's what the charge is. So if you have 2 of the same charges, they are going to repel, and opposite charges attract. So the example I gave just a second ago, where you have a positive nucleus and negative electrons, those are going to be attracted to each other because they have opposite charges. If we talk about electrons, say, let's even talk about valence electrons in the same energy level, they both have negative charges and they are going to repel each other. And it's not just what the charge is, but it's how big the charge is. The greater the charge, the greater the force of attraction or repulsion. So if I have a positive nucleus attracted to a negative electron, I have a certain sort of attraction. But if I have a lot of positives attracted to a lot of negatives, the magnitude of the charge is larger, and there's going to be more attraction between those pieces. All right, so Coulomb's law has to deal with the charge, and the second thing is the distance between the charges. Now, you know this if you have ever played around with magnets. If you have magnets really far apart, there really is no attraction or repulsion between the two. But as you bring the magnets closer to each other, you're going to start to feel either the force of attraction or repulsion. The same thing happens with oppositely charged particles in an atom. The greater the distance between the electrons and that positive nucleus, the less you have a force of attraction, the less the attraction force is. If they are closer together, the force of attraction is much greater. All right, so Coulomb's law, you just have to remember two things. It's the charge, both what it is and how big it is, and the distance between the charges. Let's see how that plays out as we look at some like the first 7 elements of the periodic table. So here we have hydrogen with its one little proton, one little energy level that contains one little electron. And we have a certain amount of attraction here. Well, let's now look at helium. Helium has the one energy level, but it has 2 protons in the nucleus attracted to those 2 electrons on its one little energy level. Because the charge magnitude has increased, the force of attraction between the electrons of helium and that positive nucleus is greater than that of hydrogen. And so what ends up happening is helium's a little smaller than hydrogen. Now, if we go to the third element of the periodic table, we have 3 protons in the nucleus, but we also have 2 energy levels. And now these valence electrons for lithium, it's one little valence electron, is on the 2nd energy level away from the nucleus. So there is a greater distance between the charges, which allows the atom to be larger. There's less attraction between those than there would be for like hydrogen because the electron's closer to that positive nucleus. Well, let's look at the next element, beryllium, element number 4 on the periodic table. It has 4 protons in its nucleus. It's very similar to lithium where it has 2 energy levels. But these electrons of beryllium are more attracted to the nucleus than the valence electrons in lithium are because beryllium has more protons in the nucleus. So the magnitude of the charge is greater, which causes the force of attraction to be greater, which pulls that electron cloud in just a little bit. And so beryllium ends up being smaller than lithium. If I go to the next element over, boron, it has 5 protons in the nucleus, still 2 energy levels. But we now have a more positive nucleus. So the magnitude of our charge has increased again. And so these valence electrons are more attracted to the more positive nucleus of boron than the valence electrons of beryllium or lithium. And since there's more attraction, the electrons are pulled in a little closer. All right. And then if we look at carbon with 6 protons, it has 6 protons in its nucleus. Again, a more positive nucleus, so the magnitude of the charge has increased, which means the valence electrons of carbon on that 2nd energy level are more attracted to the nucleus of carbon than they would be for boron or beryllium or lithium. And so since there's more attraction, those electrons get pulled in a little closer. And if we talked about a nitrogen, which has 7 protons in the nucleus, still 2 energy levels, we would find that nitrogen would be even smaller than carbon because, again, the magnitude of the charge increases. And so what we can kind of see from this is a little some of the trends of atomic size. And so we would measure the atomic size through the atomic radius. And the way we do that, it's two identical atoms that are bonded together. We're going to have to do that because it's kind of hard to tell where that electron cloud ends. So it's hard to just get a straight radius. So what we end up doing is taking two identical atoms that are bonded together. The nucleus is really dense and easy to find. And we measure that distance, and then we just go halfway in between it. And that's our atomic radius, which again is an indication of atomic size. The larger the radius, the larger the size of the atom. And here you can kind of see, expanded on that the atomic radius as you go across, or the size of the atoms, decreases as you go from left to right on the periodic table. They just get smaller and smaller. Again, that would be because you've got a more positive nucleus. And so that charge magnitude is increased, pulling that electron cloud closer. As you go down a group, the atoms get larger because you've got more energy levels. So the distance between the charged particles are greater, and so they're less attracted.